Hi, this is Kevin from the Mathsaurus, and in this video we're going to look at question 8 from the Step 1 mathematics paper from 2018. This is a really nice question, really tests whether you understand the mechanisms of the methods you know about differentiation and integration, and whether you can apply those things in a sort of slightly generic context. So we start with these functions and we're told s of 0 equals 0, c of 0 equals 1, and probably immediately a lot of you will look at that and think, oh, maybe these are just sine and cosine. I know sine of 0 is 0 and cosine of 0 is 1, and they've called them s and c. But we very quickly realize that they're not quite sine and cosine, because we're told that s primed of x is c of x squared. So if it was sine, it would just be cosine. And that the derivative of cosine is not just minus sine, but minus sine of x squared. So there's definitely a hint in this question that a lot of the things that are going to happen are going to be quite similar to things that you might have done with sine and cosine identities and derivatives, but they're not the same function, so we're going to deal with these in general. So in part 1 it says, show that s cubed plus c cubed is constant, and deduce that the sum of the cubes is equal to 1. So instead of the usual result with squares, we have sine squared plus cos squared is 1. Here we've got s cubed plus c cubed equals 1. So okay, so to show that it's constant, what I want to show is that its derivative is 0. Would be the most obvious way to go about this. So if we differentiate s of x cubed plus c of x cubed, then I'm going to have to apply the chain rule and get 3 times s of x squared times s primed of x, and then I'm going to get 3 times c of x squared times c primed of x, and then I guess we can choose which way around I want to try and use this result. I've got s of x squared here, so I can say that that's minus c primed of x, and I've got c of x squared, so that's s primed of x, so I've got minus 3 of it, of this product of the derivatives, plus 3 of that product, so that's 0. So that means that s of x cubed plus c of x cubed is constant, its derivative is 0 everywhere, and in particular we also know that s of 0 is 0 and c of 0 is 1, right? So actually s of 0 cubed plus c of 0 cubed is just 0 plus 1, which is 1, so actually the constant that this is equal to must just be 1. Okay, right, so that's part 1. Part 2, show that the derivative of this product is 2 times c cubed minus 1, and then we'll do something equivalent for the quotient. So really, we just have to apply the product rule here. It's fairly clear at the beginning of this question exactly what we have to do. So I just get s primed of x times c of x plus s of x times c primed of x, applying the ordinary quotient rule, and then I know that I've got these results about s primed and c primed that I'm given. So s primed is c of x squared, so this becomes c of x cubed, and c primed is minus s of x squared, so I get minus s of x cubed. Not quite what we're looking for. We want 2c of x cubed, so I can use this result that we've got here and just rearrange this to say that means that s of x cubed of course is 1 minus c of x cubed. So you see, we're doing the same sorts of manipulations we do with trig identities, with sine squared plus cos squared is 1 and all that sort of stuff, and the double angle formulae and all. We've done all those identities, so it's really testing whether you're familiar with how to do those things without just giving you examples of them, right? So I replace s of x cubed here with 1 minus c of x cubed, and then I just get 2 times c of x cubed minus 1, exactly as we wanted, right? And then it says do the same thing for the quotient, so it wants us to look at d by dx of s of x over c of x, and again, this is a bit like when you do the proof of how to differentiate tan, and that you get sec squared, right? So I'm doing sine over cosine, so the algebra is going to work out in a similar way here. So I just apply the quotient rule, so I get c of x times s primed of x minus s of x times c primed of x, all divided by c of x squared, which again by the results we're given about the derivatives at the beginning, this is c of x cubed, this is minus s of x squared here, so I get plus s of x cubed, and I divide that by c of x squared, and our fundamental identity is that s cubed plus c cubed is 1, so this is 1 over c of x squared, so actually we've got a result very much like the derivative of tan x is sec squared x, as we're used to. Okay, right, so part 3, we move on to doing some integration, and I think people probably find the integration side of this question harder than the differentiation, because they also find integration harder than differentiation in general. A lot more techniques, a lot more decisions as to which ones to employ and how to go about it. Integration is generally harder. So firstly, integral of s of x squared dx. Well, this one at least is not too bad, I think, because we're told that minus s of x is the derivative of c, right? So actually, so this is just the integral of minus c primed of x. Okay, so if I take the integral of the derivative of something, I'm just going to get that thing back, right? So so I'm just going to get here then minus c of x, and this is an indefinite integral, so I should add some sort of constant. You can give it a letter. I would not advise c here because that's the name of one of the functions. You could call it k. I'm just going to write constant. Next one is s of x to the 5, and here we have to be a little bit more creative, and so you can think about different ways of approaching this. Can I recognize this as the derivative of something? Otherwise I'm just going to have to split this up the way we often do with trig integrals. So I'm going to take out here, and so we'd often, if this was sine and cosine, I would think about taking out an s squared, so I could use the 1 minus cos squared identity. Here it's cubed. Oh, I'm slipping into sine notation, which I shouldn't use. Like, you know, to write it as s cubed of x, which probably you'd get away with here, but let's stick to the notation. So s cubed of x times s squared of x. I've ended up with the squared as well, but it's this cubed one that I'm interested in here, because that one I can write as 1 minus c of x cubed by our fundamental identity here, multiplied by s of x squared. So I've got one integral here, s of x squared, that we've just done, and then I've got this other integral, which is the integral of c of x cubed times s of x squared dx, which I hope I might be able to get at somehow. Okay, so, you know, as an aside here, why is this sort of thing going to work? It's a kind of reverse chain rule thing, right? Because we know that c primed of x is equal to minus s of x squared. So if I differentiate some function of c by the chain rule, I also get an s of x squared outside of it, right? So in particular, I do the same sort of thing I do with the reverse chain rule integrals. You know, if this was like the integral of cos cubed of x times sine of x, you'd say, okay, that's, you know, that's something to do with cos 4 of x, and I just have to worry about what constant I put in here, right? So here, you know, if I differentiate, it's hard not to write cos. If I differentiate c of x to the 4, I get 4 times c of x cubed times the derivative of that, which is 4 times c of x cubed, and the derivative is minus s of x squared. So actually, look, I've got exactly what I wanted here, up to a factor of 4. So if I multiply by a quarter, then we're done, right? If I put a quarter in front of all of this, that would go away. So I get for my s squared the same as I did before, so minus c of x for that one, and then let me be careful with the sign here, so I'm going to have to do plus 1/4 c of x to the 4, because if I differentiate that, I get exactly I get the minus out here that I want. And again, let's have a constant for completeness. Okay, so a little bit trickier there, but we're following some of our instincts from differentiating trig functions and trying to apply them in this context. Okay. Right, so part 4 then, it says given that S has an inverse function, use a particular substitution. So we're actually given at least a little bit of a hint here as to how to go about this, and we want to integrate 1 over 1 minus u cubed to the 2/3 du, and using this substitution, right? So that's u equals s of x, so that means du by dx is equal to, so s primed of x here, which is c of x squared. So using my slightly informal substitution notation, I'm going to replace du with c of x squared dx. So this becomes 1 divided by 1 minus s of x cubed to the 2/3 multiplied by c of x squared dx. 1 minus s of x cubed is c of x cubed, it's our fundamental identity. So I've got c of x cubed to the 2/3 times c of x squared dx. Cubed to the power of 2/3 is just squared, so I've got 1 over c of x squared times c of x squared, so that's just the integral of 1 with respect to x. So that's just x plus a constant. So given that I can invert this function u equals s of x, that would mean that x equals s inverse of u, and then we get exactly what we want to do here, s inverse of u plus a constant, as we were asked to do in the question. Okay, so so that part, I think, we're given the hint, so shouldn't be too bad. But then in part 5, we really have to do our own thing and work out what we're going to substitute, and how we're going to sort that out. But the functions don't look too different to the ones we've just been working with. Okay, so my first instinct here is really just to use the same substitution, right? So let's just try again. U equals s of x. So we get again that du equals c of x squared dx, right? Because why not? I mean, it's the same sort of thing. I've got to at least try this, and if this doesn't work, maybe I can try something more complicated. But let's not make things harder unless we have to. So let's see if this works. I get the integral of 1 over 1 minus s of x cubed to the 4/3 this time, and I get c of x squared dx. So we know what happens here. This 1 minus s of x cubed becomes c of x cubed. This time I raise it to the 4/3, so I get the integral of 1 over c of x to the 4 times c of x squared dx, and this is just the integral of 1 over c of x squared dx, right? And that's when you remember that actually that's something we differentiated earlier, right? We did this question earlier on, and we noticed that the derivative of this tan looking thing was 1 over c of x squared. So if I'm integrating 1 over c of x squared, I just get this tan looking thing. Can't call it tan, but it's in a bit of innuendo, as you say it there, that this is tan, but it's just s over c, and we're going to add on our constant there. Okay, right. So that's worked, and let's try the last one. So this time we want to do the integral of 1 minus u cubed to the 1/3 du, and we've been lucky with this substitution so far. I've got the same sort of thing again, 1 minus u cubed to the 1/3. I don't see any reason to change strategy at the moment until it doesn't work. So I get 1 minus s of x cubed to the 1/3 times c of x squared dx. So this gives me again, c of x cubed by the fundamental identity to the 1/3, so that's just c of x multiplied by c of x squared, so I have to now deal with c of x cubed. And I guess this is the hardest bit. I thought about this for a little while and then looked back to my previous answers and thought, well, hang on, we've just used this result. What about the other result in the part of the question there? We showed that the derivative of s times c was 2c of x cubed minus 1, right? So that thing that we have, we're trying to integrate here, c of x cubed, I've got an integral result that looks a bit like it. Okay, so let's just get that in there, right? So I want to do the integral of 2c of x cubed minus 1 instead. Of course I can't just replace this, but if I took half of this, then that would give me the c of x cubed, and then I'd have minus a half, so if I just also add on the integral over a half dx to balance that out, then that looks good. Right, so by the result earlier, this is just 1/2 times s of x times c of x, and this is 1/2, just 1/2 x. So I suppose they're allowed a constant. Now I'm not actually done with these questions, right? And I've waited for the same moment to do both of these, because my integrals here were to do with u, and I've got an answer to do with x. So I do need to go back and replace these. Right. So the s of x is easy because that's just u. The c of x, again, we're going to have to use that fundamental identity that c of x cubed is 1 minus s of x cubed, and then take the cube root both sides to say that c of x is the cube root of 1 minus u cubed. And this is the sort of thing we often do when we do sort of trig and inverse trig integrals and things like that. So it shouldn't be again, it's not a huge conceptual leap from what we're doing usually, but it is important to finish here. So this is u divided by the cube root of 1 minus u cubed, and then I add a constant, and in this one I've got a half u times the cube root of 1 minus u cubed. I mean, you could write this as a third power if you like. This notation is a little bit messier. And then my x is again just u is s of x, so x is s inverse of u, assuming that inverse exists again, plus our constant. And then I think I am done. Okay, so great step question, this one. It's kind of interesting that we can do these integrals using these functions that look a bit like sine and cosine but aren't quite. Really good, test of not just whether you've learned the rules for sine and cosine and differentiation and integration, but also whether you've really picked up the underlying methodology there. So hope that was useful. Let me know in the comments if you've got any questions or suggestions or anything else. Do like and subscribe and all of that sort of stuff if you're finding it useful, and I will put all of the videos I'm doing on this paper into a playlist so you can see them all there. And don't forget, there's the website where all of this stuff is better organised, and you can see the other step questions that I've done from other papers there too.